Hello, this is Hilary Weller. This is a short video introducing semi-Lagrangian advection. This is a type of advection scheme that's used widely in weather forecasting models. The point of semi-Lagrangian is that it's designed not to have time step restrictions associated with the current number, which is u delta t over delta x. So you can take a large time step, even when there's a large velocity, and if you've got high resolution, if delta x is high, which will make it more efficient, and it's an explicit scheme, so you don't have to invert a matrix to achieve this level of achieve large time steps. It's used by the UK Met Office and by the European Centre for Medium Range Weather Forecasts. And the way it works is, in order to calculate a new value of a dependent variable, for example the temperature, you look upwind to see what the value of that variable is upwind. So you look upwind to see what the temperature is upwind, for example, to where it's come from. So this is an example of advection of there's something being released here. For example, it could be a pollutant being released, and then it's advected around by the winds. So the way semi-Lagrangian would work is that in order to see what's coming, so for example if you're here, you see what the wind is and you look upwind and look at the concentration upwind, and then the next time step you work out what the value should be based on what's upwind. Now I'm going to describe exactly how this works in one dimension. So remember the CFL criterion. The domain of dependence of the numerical solution must contain the numerical domain of dependence of the original PDE for stability. So we want an explicit scheme, and so in order to allow long time steps, we must construct the numerical domain of dependence to contain the physical domain of dependence. So remember the linear advection equation, d phi by dt plus u d phi by dx equals 0, and we know in one dimension for constant u, we know an analytical solution for this equation. So we use this to write down the semi-Lagrangian scheme. So phi at position xj at time level n plus 1 is going to be must depend on phi at time level n, but at a different position at xj minus u delta t from the analytical solution at time level n. So we call this is the departure point xj minus u delta t, and we call it xjd. So xjd is equal to x minus u delta t. So for example, if this is showing time versus space, and these are all the positions where we need to work out what the new phi is. So here's phi at position xj at time level n plus 1. So we go back to the previous time level along a trajectory and find out where the departure point is. And we need to find out, it's not going to fall exactly onto a grid point. We need to find the grid points either side of that departure point. And we're going to need to interpolate from these. So phi is going to be known at these values, xk and xk plus 1. We're going to need to interpolate from these points onto this new point xjd, the departure point, because we're not going to know the value of phi at that point. So first of all, we need to find these values k, the points that surround the departure point, such that xjd is between xk and xk plus 1. So you can find the value of k, and you can use the function floor of x, meaning the integer below x or at x. So how are we going to find k? We know what xjd is, and we know that x is equal to xj is equal to j times delta x. We need to find k. So k is going to be equal to the... You can pause the video at this point, see if you can work out what k is going to be. K is going to be, if xj is j times delta x, k is going to be the integer part of, or the floor of, xjd. Divided by delta x. And so then if you can do xj divided by delta x, that'll give you j, and u delta t over delta x is c. So this is an equation for how to find k. And then we need to interpolate from the points, surrounding points. For example, you might use 4 of them onto xjd. If you're using 4 surrounding points, you could use cubic Lagrange interpolation. Another exercise, in order to do this interpolation, you'll need to know whereabouts in this range this xjd is. So you can use an interpolation parameter beta, which is defined as xjd minus xk divided by delta x. So try to find an equation for beta, which is in terms of j, k, and c, given that xj is equal to j delta x and that c is equal to u delta t over delta x. Pause, see if you can work out that formula for beta, and I will show it now. Beta should be equal to j minus k minus c. So the advantage of semi-Lagrangian is it is an explicit scheme without a current number restriction. A problem is if you do semi-Lagrangian with interpolation like this is that the advected quantity is not conserved. There are conservative versions of semi-Lagrangian which I'm not going to describe here, but they're not necessarily perfect. Thank you very much. In the next video we're going to look at some other alternative schemes.